Okay. Okay, everyone. So, as you already do know, this is the scientific talk. So, today we are having Bhaskar Singh Rawat, sir, who is a research fellow at IIT Ropar. How many of you ever heard about her? So, he's just going to take a very interesting topic today. And it is going to be kind of interactive type of things. So, first of all, sir is just going to cover the topics. Then you can just interact with the sir. Okay. So, this is usually any scientific talk session is going to be had. So, first of all, I would like to invite the Bhaskar sirs. So, please continue the session and thank you so much for joining us at very sort of notice. Thank you, sir. Please continue. Let me make you the host. Yes, yes, sir. And everyone, your mic could be off. Okay, just mute your mic at least till the session. And what you can do after the session get done, you'll be going to allow to ask any questions. Okay, you can just raise your hand and then you can ask your doubt one by one. Okay, I hope this will be clear.
Okay, am I audible to everyone?
Yes,
Just give me thumbs up if I'm audible to everyone.
Yes,
Okay,
yes.
okay.
You're audible.
Looks like I'm audible. So I'll be quickly sharing my screen. Yeah. Oh, so is this visible to everyone? My screen is visible. Like, can you see the slides? Give me thumbs
yes,
up.
sir. Yes, sir. It's visible.
Okay, okay. So okay, let me start with this time. So, a very good evening, everyone. My name is Bhaskar Singh Rawat. As sir has already introduced me, I'm a research fellow at IIT Ropar, and today for this session, I'll be covering this topic EMRIs with black holes. So, actually going through the presentation, I would like to start with this quote, which is written by me. It states, "Nature is not absolute, but relativistic and probabilistic. What is required is to understand it." So, what this quote actually says is whatever the nature or the environment we are living, it's not absolute. Nothing is absolute. Nothing is, you can say, have a same perspective. Everything is relativistic, means uh, everything, whether you talk about velocity, whether you talk about anything, everything appears to be relativistic and probabilistic. So relativistic term is here to define this GTR and STR, general theory of relativity and special theory of relativity, and this probabilistic kind of quantum mechanics. So nature is not classical, but it is quantum mechanics, and it is full of this relativistic physics. And what is required is to understand it. And we need researchers, we need individuals to actually understand the nature in this perspective. So, so how am I going to go through this presentation? So I will be first presenting these basics which are required to be understood, and then afterward I will show you some of my results which I have worked over. And so yeah, let's go with this. So what are EMRIs? So EMRIs stands for Extreme Mass Ratio Inspiral Systems. So it basically has two important concepts. The first one is this extreme mass ratio. So what are extreme mass ratios? So these are the systems where mass is very heavy and the other mass is very small. For example, we have a supermassive black hole and a stellar mass black hole. So supermassive black hole can go up to like 10 to the power 7 of solar masses, and this stellar mass is like up to 10 to the power 1, 10 to the power 2 solar masses. So when a body has a very huge mass and the other body has a very small mass, we call these kind of system as extreme mass ratio systems. The other thing is which is written here is are the inspirals. So what are inspirals? So basically, when we study gravitational wave, so how do we study gravitational wave? Gravitational wave basically uh, is the chaos which is the chaos in the motion which creating this wobbling effect in space time. And this wobbling effect is basically we classify into three different categories. When the motion of the bodies are kind of uniform, means they are not either coming close to each other, not going far from each other, they are kind of uniform and the radius is uniform, we call these kind of systems as inspirals. Okay, and the other kind of when those uniform system, when the radius is decreases of those uniform radius, they together and have this phase where they both are close to each other, and that phase is called as merger here. And the last phase is called as ring down. Ring down means when two bodies merge together. This they are completely, now you cannot distinguish between two bodies. This phase is called as ring down phase. So as you could have already predicted, that we are interested over extreme mass ratio in spiral systems. So we will be talking about systems where the motion appears to be almost same, almost uniform. There is no merging happening. There is no ring down phases, just the spiral phases there. So, and one body is like heavily massed, and the other bodies like this has a small mass. So what are the mass requirements which we will be considering? Is this 10 to 7 solar masses and plus this 10 solar masses. So what are the other like EMRI black hole systems? So the systems are like supermassive black holes, stellar mass black hole. This is a like one binary system. The other can be supermassive black holes and a blue supergiant star. And the third one can be supermassive black holes and main sequence stars. So our sun is like main sequence star. But for this very specific study, we are interested over this first scenario where we will considering the first first object to be as a supermassive black hole, and the other can be a stellar mass black hole or any neutron star that could have a mass to 10 solar masses. So since I already said that we will be considering both the system to be heavily dense systems, like black holes are very dense objects in the universe. So we cannot just directly go and study the analysis by using the standard methods we have, because the black holes have their own properties of they have a great gravitational pull, and that gravitational pull somehow varies the trajectory which we would have gotten from the standard methods. So we imply some approximations. So this one approximation we have implied, since we have considered the mass in such a way that one body is like very massive, tends to have 7 solar masses, and the second one is very small, 10 solar masses. So this test mass approximation is viable, since so we can say that okay, since the second body is very small, so its motion is going to be almost like the one which should be getting from the traditional methods. So what are the traditional methods? We will be covering the traditional method in the later slides. So this is like, what is this test mass particle? When the mass of the second body is very small, so that its motion can be actually analyzed by the standard methods which we have in the general relativity. So it makes like a complete sense here. So we'll be talking about what is our black hole here, and about this PFTM. It might be a little like advanced for some people, but I try to make it as lucid as possible. So it's a charged black hole. So what happens is, like, historically, after Einstein gave its general theory of relativity, people tried to solve this Einstein question and gave some solutions. So the first solution, which was given by Schwarzschild, and that's why we called the first solution of the black hole as Schwarzschild black hole. And it turns out black holes are extremely, they can be very massive, and they were unimaginable gravitational pull that even light cannot escape them. So if like I have a black hole and it lies, a light goes near to it, the light will show a deflection. It will show a deflection which we call as gravitational lensing, or it might go inside the black hole. So even it has an extreme gravitational pull that even light cannot escape from it. Well, I believe I cannot see your chats and all. So like if you are guys having any doubt, we will resolve it at the end of the session. Okay. So where I was. Okay. So, and the other solution after this Schwarzschild, some other solutions of black holes also came. So there is this another solution which is called as charged black hole. So what this solution manifests, it manifests the black hole having some charge. So it states that the universal black holes have some charge, and that charge provides them a capability to interact with the electrons, protons, and other charged bodies. So for this study, we will be considering a black hole to be charged, and it has the environment of PFDM. So what's this PFDM? So PFDM stands for perfect fluid dark matter. So what we are considering our supermassive black holes as charged black holes, and they are surrounded by the dark matter environment. And this dark matter is sort of having the behavior of fluid. A perfect like in physics, what we meant by perfect, why we are using the term perfect here. So perfect basically defines that the fluid, it behaves like an ideal gas. I believe that all of you might be knowing this ideal gas. Like it has like no interaction between the molecules is there, and the conservation, all the conservation symmetry properties are there. Like the energy conservation is there, the momentum conservation is there. So sort of and for the perfect fluid, even there is no viscosity. So it's like there is no internal friction between the fluid. You can say like that. So we are considering our dark matter to be as perfect fluid. So it's like it's a very basic model, it's a very standard model. And if you're like very much interested into understanding why how we came up with the solution of the stars black hole and this how we implemented this perfect fluid dark matter, I would recommend you to go with this second reference, which is this written by this a very good paper on charged black holes and this perfect fluid dark matter by Anish Das. So you can go with the second reference. So these are the mathematical equations. So I won't be covering mathematical equations in this presentation very much, since I believe like majority of students or people in this meeting aren't relevant with the required mathematics for this presentation. So I would just quickly explain you what does this mean. So this defines the space-time. So what's the space-time? Einstein has said it. There is no space and time, it's space-time. So we don't consider space and time to be as individual quantities, we consider it to be a one quantity. So this is the metric for the space-time. What's a metric? So it defines the property of the space-time. So like how my black hole is going to be, how it like curves the space-time. So this particular equation defines this, and this FR it is like it is when we basically put this equation in the space-time equation, and this FR has, like you can see, it has this capital M. The capital M defines the mass of the black hole, and this Q square defines the charge, and this gamma is the perfect fluid dark matter, and R is the distance, from the point of interest, like to the point of interest. Sorry. Next, so what our space-time model is, so we have our black hole has a charge surrounded by perfect fluid. So it is defined by three parameters. It has mass, it has charge, and it has perfect fluid dark matter. So here I have shown some black hole required stuff. The first is this horizon plots. So what are horizon? So every black hole has a boundary, and that boundary we call it as horizon. So horizon is a point of no escape. What does it mean? Like if anything, even a light, any particle touches this horizon, it cannot go back from the black hole. There is no way we can like get that thing back. So if I have a black hole and something came and touched its horizon, so we cannot get it back. It will go inside the black hole. It might due to singularity, it might stay there. It depends upon the frame of reference. So horizon plot. So what we find out, so it is a plot between charge and the radius, horizon radius. So what we found is like as I increase the charge of the black hole, if I let's say I have a black hole, and if I go and increase its charge, then its horizon radius is decreasing. Okay, so what kind of behavior do we get? It's the both. If you add both the plots together. So what was the behavior? The behavior was, if I go and increase the radius of the black hole with the charge, if I go and increase the charge of the black hole, the radius is decreasing. Okay, and what happens with this perfect fluid dark matter? If the environment of the black hole, where this perfect fluid dark matter, which is defined by gamma here, if I go and increase the value of gamma, what will I find is like my horizon or the radius of the black hole is first decreasing, and after a constant value it starts increasing. So this particular behavior was completely unknown and mysterious, and the reason to this is because what is this dark matter? Okay, so the concept of dark matter was actually given by the analysis of Rubin, if I am if I'm correct with my knowledge. And what was it? It is a parameter which is not observable. It doesn't even interact with light. And it doesn't interact with anything, not the light, not the charge, nothing. So, but it interacts with the mass with gravitational force. So there is no electromagnetic interaction, there is no strong, there is no nuclear, nothing, no interaction, just the gravitational interaction is there. So I have, like, you can say, some sort of imaginary mass is there in the universe which interacts with this ordinary mass by gravitational force. Other than this, nothing. So you can say that if I go and increase the gravitational force, like if I'm increasing this perfect fluid dark matter parameter, the gravitational force should also increase. So one can, like, think, if I'm increasing this extra gravitational force to the black hole space time, either the radius should be decreasing or it should be increasing. The behavior should be monotonous. But what kind of behavior we are getting here? We're getting that if I increase the dark matter parameter, the radius starts decreasing and then it starts increasing after a critical value. So it was something which was unique about this perfect fluid dark matter. And sort of my work is basically to understand this same property for the periodic orbits and for the gravitational waves. So I will, like, cover that as well. So here you can see this perfect fluid dark matter parameter. So this parameter gamma is directly proportional to density. But what this equation states that this my perfect fluid dark matter is basically sort of associated with the mass of the perfect fluid. So, like, if I increase the gamma, that means the mass of the dark matter, which is the environment of the black hole, is also increasing. Now, next, this other equation is the horizon radius equation. So we basically numerically solve this equation to get these plots to understand the nature of the horizon. And this RHM is the, I said, na, see, if I go and increase this BFDM with gamma, my black hole starts, the radius of the black hole starts decreasing. So this is the minimum value. This RHM is the minimum value, and you can see this minimum value depends on mass and charge Q. And E is the exponential term. And this gamma, which is the critical value here, the critical value, at what gamma I will be getting the lowest value of my horizon radius. This is the expression for the gamma. Okay, so now the next topic is this periodic orbits. So like, what are periodic orbits? So I believe we all know what are periodic orbits. So, like, these are the orbits which have, like, which can be defined by the property called as time period. So, like, after a certain interval of time, the overall motion starts repeating itself. So these kind of orbits are called as periodic orbits. And so what are the periodic orbits which we are talking here? So you can see these are the periodic orbits. So we are going to get these kind of periodic orbits, and these orbits have two phases. You can see zoom phase. So what's this zoom phase? Okay, what kind of orbit is this? So what happens is, like, let's say I have my a supermassive black hole right here, and I have my stellar mass black hole right here. So what happens is, like, my stellar mass black hole first comes near the black hole, near the central black hole, and starts rotating like a chaotic rotation. Then it goes back, like, it goes very far to the black hole, then come back and starts rotating chaotically near to the black hole, then goes far, then comes, then, like, this kind of behavior is there. So this is how we define it. This particular orbit is called a zoom will orbit. So what's the zoom? So when it goes like away from the black hole, it is called a zoom phase. Then it comes near the black hole, and this chaotic motion is there, which is called will, and then goes back, and then this kind of motion is repeated. So these orbits are called as periodic orbits. So these periodic orbits can be manifested in between of two orbits, which we call as ISCO and MBO. So what's ISCO? ISCO means this innermost stable circular orbits, and this MBO is the marginal bound orbit. So like, I'll quickly explain you what ISCO and MBO is. So MBO is basically a circular orbit created by any like test particle which is very close to the black hole. So the possible closest stable orbit that can be created, that can be manifested around a black hole is MBO. You can see this MBO red defined by red, and this ISCO is basically the, well, it is said to be innermost stable circular orbit, but it's basically like MBO is very close, radially very close to black hole, and this ISCO is like, exists, has a way more radius than this MBO. So ISCO is the like outermost stable orbit, and this willing part, which is this the part which goes very close to the black hole, occurs in between MBO and ISCO. And the zoom part, basically it can go like way beyond radially way beyond than this ISCO. So this is the behavior. So how do we define this zoom wave periodic orbit? So in terms of ISCO and MBO, we say that if the energy of the particle, let's say by this test stellar mass, very small black hole, if this small black hole has energy which is in between of energy requirement for MBO and ISCO, and angular momentum in between of energy, the angular momentum requirement for MBO and ISCO, if it is in between of them, then then only these periodic orbits will manifest. Okay. Other than these are the you can say equations required to find out the radius, energy, and this angular momentum for MBO and ISCO. So this is the taxonomy about the periodic orbit. Okay, so the first very important question is why the periodic orbit? I mean, if periodic orbit are there to exist in the universe, then the possibility to get a periodic orbit around a black hole is going to be very small. Okay, then the question naturally arises, like, why we are interested into periodic orbit? Why not the general orbits? And the answer to this question is like periodic orbit will most like they will be creating this periodic gravitational waves. And if we somehow getting this periodic gravitational wave, then there is this high chance that we will be able to observe those gravitational waves. Now, again, it contradicts basically my first statements. Like, if periodic orbits are there and like the probability of getting the periodic orbit is very low in the universe, then why we are into the gravitation of the periodic orbit in the first hand? And the answer to this question I will explain you later in the last slide. Basically, we consider this approximation called as adiabatic approximation, which has this association with this. So we'll discuss this later. So about this periodic orbits, so Levin, there is this great paper by Levin. You can see this. This is the name of the paper, a periodic table for black hole orbits. So what he defined? Wait a minute. Wait. So what Levin defined? So he basically termed the different kind of periodic orbit in with the help of these three numbers. So these numbers are Z, W, and V. So what is Z? Z is zoom number. So it basically defines how many zooms I have. Let's say in this scenario, I have 3 zooms. Zooms means the outermost trajectory. W is the will per zoom. So for one zoom, how many wills are there? So there can be 3 wills, 4 wills, and 4 or 5 wills. So you cannot actually find out how many wills for this particular diagram, since you can say we first know the will and then we create these orbits. So if somebody is like very good and have a very good eyesight, then he can go and count these wills, but for me it's kind of impossible. Okay, this W is the vertex number. So what this vertex number defines? It defines that after this one zoom, where the second or like second zoom will be. So let's say if it is my vertex 1, means the particle starts its orbit from here and it starts willing, then where it will go? Will it go to vertex 2 or will it go to vertex 3? So this is defined by vertex V number. Okay. After that, we have this Q value. So Q value is a mathematical value which is associated with this zoom will periodic orbit. So it has no physical significance. It's just a mathematical value that actually connects this structural property, which is defined by this ZWV, because they define the structure of the orbit. to the energy and angular momentum of the orbit. So this value right here, you can see this q value. This q is actually equal to w plus v by z. So this is a number, and this q can also be related with this angular momentum and energy. So basically, one have to find out what are going to be the energy and angular momentum for the periodic orbit. Let's say for a specific structure of periodic orbit, one has to solve this integral, which is, to be very honest, is very difficult. Like you cannot go and directly solve this integral. That's why we do plotting here. I will show you this q value plotting later in the next slide. And to the right hand side, you can see some periodic orbit. So for 110, we have one this we have this one zoom and one will per zoom, so it goes this, and zero vertex, so it goes this and come back same 120. So it means that we have one zoom and two wheels per zoom, so it will go and starts wheeling two times and then come back. For 212, you can see similar kind of behaviors for 212, 312, and 412. I also like to term these orbits as floral orbits because they looks like uh, flowers. That's why. Okay. Well, next is this. What's the motivation? So to be very honest, these kind of orbits, the capability to observe these orbits through gravitational wave, is not possible right now because currently we have LIGO, uh, and LIGO doesn't has the capability to observe low frequency gravitational wave, and gravitational wave associated with these periodic orbits are low frequency gravitational wave. But there are certain observatories which are in the testing phase, such as this LISA, Laser Interferometer Space Antenna, and it is a collaboration. It is a collaboration between European Space Agency and this NASA, and they are it's in testing phase. So most probably by 2030 or 2035, I believe it will be in the workable phase. So it is said that these observatories, they are space-based observatories. So they have this capability to observe these low frequency gravitational waves. So this is the reason where this low frequency gravitational, this blue region where this low frequency gravitational wave occurs. It's in between of 10 to the power minus 3 to 10 to the power minus 1. Here you can see, and this red line, it defines this uh, EMRI system, harmonic EMRI in spiral systems. So yeah, their frequency is between 10 to the power minus 1 to 10 to the power minus 3 hertz, and their amplitude requirement is 10 to the power minus 20 to 10 to the power minus 21. Kind of basically these kind of requirement is not observable right now by LIGO, but by the space-based future observatories, it will be observable. So that's why a lot of study right now is going on in this domain. So different kind of black hole metrics are being analyzed to study different kind of low frequency gravitational waves. So what I have written here why periodic orbits. So yeah, why periodic orbits? So basically periodic orbits have this systematic analysis of theoretical systematic analysis. We have as I have said that we can name these periodic orbits, and we can sort of define this mathematical value called as q value, which can be connected with this structural numbers and which provides this bridge between structural numbers and this what do you call this energy and angular momentum of the orbits or the particle providing this making this periodic orbits. Other than this long run observation, as I said, that periodic orbits will have periodic gravitational waves, and these periodic gravitational waves have this they would have high possibility to be observed for a long period of time, because since the motion is uniform, the gravitational wave is uniform, so we can observe it for the long run. And the third line is important. It states that an approximate study for non-periodic orbits in their gravitational wave. But what happens is like by actually analyzing the periodic orbits, we are getting the idea about the non-periodic orbits as well. Like what kind of gravitational wave for the non-periodic orbits will be, we can get this idea. Although the periodic orbits are not are in low probability in this in the universe, but studying them provides us this upper hand analyzing this, getting the idea about this non-periodic orbits and their gravitational wave. And that is this one reason why people are very much interested, like researchers are very much interested in understanding these no, like these periodic orbits. Okay, next. So this is the mathematical modeling. So I'll be skipping this part since it is very heavy GR. And but basically, if anybody of you would have studied this basics of general relativity, then it is not much of a big deal, and that's why I have written here. Like one can find all the requirement mathematics in chapter 8 if you're interested. You can go and like you will get these all the equations and their explanations. But I would be explaining this plot right here, which is at the right hand side. So what this is the plot between effective potential and this radius. So what's an effective potential? So my central supermassive black hole is having a high gravitational pull, and this high gravitational pull is somehow means it's affecting this my test particle, and this test particle is now having this is in the potential of this supermassive black hole. So this potential term is used to manifest the orbits. How? So what we do is like we go and calculate this effective potential, and you can see the equation of effective potential here. It is nothing but the multiplication of this Fr to the 1 plus L square by R. So this is my Fr right here. To multiply it with 1 plus L square by R, you'll get your LR square, you'll get your effective potential. Then you plot this effective potential somehow, like you sort of get this kind of plot. And this plot is basically defines, let's say if my energy of the particle is positive, it will come here, it will like goes from here, then from the right hand side I'll be considering the particle. So it will come here, and this region will be this unbounded region. And if it is less than this 0, then it will be in the region of this curvature, and this curvature will provide us a bound orbit. So I know it's very difficult for you to understand this very concept because it is itself a complete chapter in in J.C. Upadhyay's book and in the Goldstein's book. So right now it won't be possible for me to explain you everything, but like one can understand this particular quantity can be used to find out the orbits. That's it. Then like now we will be going through my research analysis. So I first did my potential analysis. So what I found it is like this figure F is of our interest. So it states that if my charge is very much like 0.8, it's a very big, like charge is based for the black hole, we consider charge in between of 0 to 1. Okay, so it's basically charge per unit mass, but you can say like charge is it is the quantity which is defined in between 0 and 1. And this gamma, which is my PFDN parameter, it is also defined in between of 0 and 1. So what my analysis finds is that like if my charge is very much means like 0.8 or 0.9, and my gamma parameter is also comparatively high, like 0.5 and 0.6, there exists this low probability of getting the energy or angular momentum required for the perfect fluid for the periodic orbit. So what it means is like if my charge of the black hole is high, and if my surrounding PFDM environment is like it has mass very much, then there is this low probability of me for getting the periodic orbit. So this was something which was new for me. Like it was very exciting, like how am I going to because there exists this very small range of energy and angular momentum for the high value of this Q and this charge and perfect wave dark matter parameter. So it becomes very exciting and challenging for me to find out that small range and find out those values of small range to the for the manifestation of this periodic orbiting gravitation. So my next analysis is the MBO and ISCO analysis. So MBO and ISCO is are the nearby orbits. As I have told you, this MBO is close to black hole. ISCO is like outermost orbit, but the state is called as innermost stable orbit. There is its reason behind it. And what I found it by analyzing them, I found that the radiuses of MBO and ISCO orbits are basically showing the same kind of behavior as we seen in the horizon behavior. So similar to the radius of black hole, my MBO and ISCO, they are decreasing with my dark matter parameter, and after a constant value, they are increasing. And it was again a very different behavior to the other models of dark matter, because we expected dark matter to give us this monotonous behavior, but here we are getting this a curvature kind of behavior. So it was very different, and I call it as like elevating and retarding behavior. So it's like retarding and then elevating. So you can say it's like elevating and retarding behavior. Then where I was, okay, about this angular momentum and this energy. So I found that my angular momentum is basically decreasing with this charge, and energy is also decreasing with the charge. And in comparatively to the this angular momentum, this PFDM. So my PF with the PFDM parameter, my angular momentum is decreasing, and with the energy, my energy is basically increasing with my PFDM parameter. So these sort of behavior with the energy and angular momentum, they are not much of very interest. The interesting part is about this behavior, this elevating and retarding behavior of radiuses with PFDM parameter. Okay, now this EL region analysis. So what is this EL region analysis? So it is the analysis of the energy and angular momentum required to manifest the periodic orbit. So here you can see for this gamma 0.5 and for this charge, so this pink is for basically very much charge, and this as the charge is decreasing, you can see. So you can basically see this region of EL is basically for a constant value of this 0.5, you can see there is not much region for me to get this angular, compare it with the first charge. Sorry, this with this first figure, you find this when the gamma is 0.01, very small, there exists a lot of region where I can get this angular periodic orbit. But for gamma equal to 0.5, my region for angular momentum and energy is very small. As I have said it before, it states that if I have a charge, if I have a black hole with very large amount of charge, and my PFDM has a very high mass, then I have this low probability, low chances of getting this periodic orbit. So, and this is the Q value analysis. So I found that my Q is basically decreasing with this. It's average after a value, it starts decreasing, and sort of opposite trend is there for energy. And so what is the use of these plots? So what we do is for, let's say, for Q is equal to 2, we draw a straight line, and this is for different value of charges, and then we see that okay, for Q is equal to 2, my value of angular momentum is this, and for here for the Q value of 2, my value of energy is this. So this is the use of these plots. Of course, this is used using computational programming, but to sort of give you the basic idea, I'm saying that we draw the straight line, stuff like that. So this Q value is as I have said, this Q value can be connected with this structural property W plus V by Z. So from here I can say, okay, like if this is like for the 4 zoom orbit, for this particular kind of periodic orbit, this is going to be my energy and angular momentum. So this is basically the reason of using, or this reason of introducing this Q value. It acts like a bridge between a structural property with the energy and angular momentum required for a periodic orbit. Okay, some fun works. So like this first work is this by Tao, this Zhao. So this first I want to tell you this particular kind of study is basically right now it is heavily done by like Chinese people are doing a lot of work in this field, and Indian people are not doing, like hardly 2 to 3 papers have been published by by Indian people, or I'll say that when all the researchers are completely Indian. So a lot of North Asian people are doing a lot of great work in this domain, and our country is working in this field. Uh, IIT Kharagpur has started, and IIT Gandhinagar has started, and this HNB Garhwal University has started to work in this domain. So if you are like interested, you can write those peoples. So they might be helpful to you. Other than this, like this third work is by this Indian people. This is a paper from IIT Kharagpur. So they analyze this kind of behavior for regular black holes. Okay, then these are the periodic orbits which are which are manifested by using this Q value, basically the structural property with the energy and angular momentum requirements. So by the 2 lines here, so the red line is for the non-charged black hole, and this purple line is for the charged black hole. So like again, I have compared different kind of these orbits for the different kind of values of charges with the different values. Sort of comparative analysis is there. And other than that, this is this distance. You can see this is very interesting here. So you can see that okay, what is this distance here? So it defines the distance, minimum distance to the maximum distance of orbit. So for this, for here, you can say my minimum distance is this, and the maximum distance is this. So it defines the distance between the minimum and maximum distance. So you can see with the charge, my distance, minimum and maximum distance is increasing. It's increasing. You can see clearly here. And for the increasing value of gamma, it's decreasing. Okay, you see, it's decreasing for the increasing value of gamma. So you can say that, okay, if my gamma is increasing, my perfectly dark matter is increasing, my orbits will be small because the minimum and maximum distance is small. So orbits will be small for the high value of this PFDM. And if I preserve this gamma and increase my charge, so opposite trend is there. So my orbits become large. So you can say with both increasing, so they're kind of balancing behavior will be there. So it depends which one is strong. Okay, about the gravitational waves. So this is this quadrupole formula for the gravitational waves. So it depends upon this. Majority of terms here are constant, like this M is constant, this this dr is constant. This dr, sorry, d is my luminosity distance. This d is constant. My mu, which is reduced mass, is constant. This eta is constant, and neta is constant. But what varying here is this phi. So phi defines the this radial. Okay, this how the angle of the radius is varying, and this r defines the radius. How the radius of this is increasing, then it's coming back and decreasing. So how the radius is varying. So we find these phi and r with the help of effective potential. If I have written the equation, okay, yeah, you can see this equation. So from this particular value, we find this t, and for this value we find phi, and from this we find r. So by solving these derivative, differential equations, because since I already know my energy and angular momentum by the analysis of this q value, so I plug these values and solve these differential equations and get the values of this phi, and get the value they get the functions, time dependent functions for the phi and r. And by plugging those functions in these equation h plus and h cross, I find these gravitational waves. So what are these gravitational? So these are not actually the gravitational waves, but the waves manifested by the detectors. So this is the way which we should be seeing from the detectors. So you can see it like the behavior. I'll start with this behavior. So what kind of behavior we are getting? We are seeing that okay, it has some of chaotic behavior and a smoothing behavior, then a chaotic behavior and a soothing behavior, and a chaotic and a soothing behavior. Now look at our periodic orbit. How our periodic orbits are. So our periodic orbits, like it has a okay, if I start from here, it has a chaotic part, and then a smooth part, then a chaotic part, then a smooth part, then a chaotic part, then a smooth part. And this can be seen in the gravitational wave. We see that okay, it has a chaotic part, so we'll call it as Will phase, and it has a like smooth part, we'll call it as Zoom phase. So clearly, my gravitational wave explains these kind of periodic orbits. It has a characteristics of these periodic orbits, and like yeah, it should be, because since they are manifested, they are the manifestation of the periodic orbit. But yeah, it's interesting to find these kind of behavior in this gravitation. So this is like you can see, okay, this is like more defined Will part and Zoom part. Okay, so about the results. So I found that, okay, I'll one by one explain the results and how we came to these conclusions. So my periodic trajectory depends upon the parameters. We see that it depends upon the q value. Q value depends upon the energy and angular momentum, and and this angular momentum and energy, they changes for different values of charge and gamma parameter. So clearly my periodic trajectories are varying with the parameters. Next is this elevating and retarding behavior. We find this behavior with this horizon radius. We find this behavior with MBO as and ISCO radiuses. So this elevating and retarding behavior is there with the PFDM parameter. Now study is consistent throughout the analysis. So this is this point. From the analysis of the periodic orbit, we find that for the higher values of charge and gamma parameters, I have low region for energy and angular momentum, and this is also, we see it for this EL region. We find the same kind of behavior in the EL region. We see that, okay, this Zoom part and Will part, it is also there in the periodic orbit, it is also there in the gravitational wave. So the study is consistent throughout the analysis. And the fourth thing is like each orbit has a unique gravitational structure. So what does this mean? You can see, okay, so this is, okay, better to see this here. For the blue part, we find this amplitude to be higher. For the red part, little small. Okay, so clearly there is a difference. You can like, based on the properties of the gravitational wave, by comparing two different gravitational waves, you can say whether the orbits have like high turning points or a high minimum and maximum distance, or like what kind of behavior is there, how many zooms are there, how many wills are there, just by looking at the gravitational wave. So every gravitational structure provides different characteristics of the orbits. So this is something which is like from the perspective of observational physics, it is kind of interesting point. Next is this gravitational wave has high frequency zones associated with the waves and low frequency zones associated with the zooms. We see it like these are the high frequency zones and these are the low frequency zones. We find these kind of behaviors. Next is this a gravitational wave lie in the observable region. So this is very important. Observable region, I mean to say that future space-based missions will be observed will be able to observe these gravitational waves, and like these gravitational waves are in between of 10 to the power of -1 to 10 to the power -2 hertz, and it is observable. So it is like interesting. So what is this approximation? The first approximation I have already told you in my first slide, which was test mass approximation. Other two approximations considered here are the adiabatic approximation and the no higher orders in gravitation. So what's an adiabatic approximation? So the manifestation of the gravitational wave, we considered the energy and angular momentum to be constant. Now think about the real systems. So the real systems, they will not have constant energy and angular momentum. Let's say I have a particle and it is near to this very supermassive, densely packed black hole. How we can say that, okay, its energy and angular momentum throughout the motion will be constant? No, it will have some kind of loss of energy, loss of angular momentum, and that's why the manifestation of gravitational wave is there. So, but why we consider it to be constant? Why we consider it to be uniform? So basically what happens, let's say I have my black hole right here, and the distance between this black hole and this my test particle is very much, and it is affected by the gravitational field. So for the one period, okay, for the first period, the variation between the angular momentum and energy is very small. Means energy and angular momentum is in loss, but the loss is very small, that for the one period, or like for the few periods, let's say 1 to 3 4 periods, we can consider this loss to be negligible. And that's how we came up with this adiabatic approximation, that the overall energy and angular momentum is almost uniform. There are some studies which actually like deeply analyzes the variation of angular momentum and this energy with the gravitational waves. And okay, so what kind of behavior we get if there is this loss of energy and gravitational wave? So you will find its amplitude starts decreasing. So you will find, okay, its amplitude here, you will see a sort of decrement in the amplitude. So this kind of behavior can be seen when there is loss. Okay, no higher order terms in gravitational wave. So, okay, in physics, like this, when we sort of go and do find the gravitational wave, so it appears to be an expansion which has so many terms. So we remove the higher order terms, and the reason to removing the higher order terms is like because the first term appears to be very dominant, which is called as quadrupole moment term. So the quadrupole moment term is very dominant. It's so much dominant that we can sort of remove, or like it is like this. I have 10 plus 0.001. So you can like you can say, okay, I will be considering it to be as 10 because it's 10 plus 0.001. So I neglect this 0.001. So we did the same here. So we didn't consider these higher order terms. And it's okay. So what will be the effect of not including the higher order terms in the gravitational wave? So the effect is basically we won't be getting the accurate accurate amplitude and accurate frequency. We sort of getting this approximated amplitude and approximated amplitude and frequency. And I believe it is fine. Like at the end of the day, the motive of me to do this study is basically to see whether we get the same kind of behavior as we are getting in this horizon plots, and we are getting the same kind of behavior with the periodic orbit and all. Okay, so like this was it about the results and approximations considered for the study, and about the discussion. Okay, so the first point is, can this study, whatever we have done, can they explain physical real black hole systems? And the answer to this question is actually no. The study done here doesn't actually define the real physical black holes, and the reason to this is because real black holes have spin; they are rotating, and I haven't included the rotation of the black hole here. So if one have to go and analyze this kind of study, then he or she has to include this rotation of the black hole. Other than that, there are a few other things like this accretion disk is there for the real black holes, which I haven't included here. Real physical systems have this extra gravitational forces, like the universe is expanding, right? And this expansion provides this extra gravitational pull. And there are few other like this. There exist few other environments. There exist particle environments and this stringly environments. There exist other environments as well, which I haven't included here. So the overall study is basically an approximation of the real physical scenarios, but it provides us sort of idea about how where this particular study lies and it can where this study can go. Other than that, future possible works. So the future works will be is to include the more models in the study, to include other dark matter parameters, to include this particle environment, the stringly environment, this accretion disk can be included. So, and this spinning black holes can be considered. Spinning test particles can also be considered. So this the study of the spinning particle is going on there in HMB Garhwal University, and other metric analysis are also going on in HMB Garhwal University. So these kind of analysis can be done. Okay, so now I believe that is it for the session. It looks like I almost took like 1 hour. Okay, so, I will be ending my slide here, and now we can go for the question and answer. So over to you, to the host who are hosting this event.
All right, I think we are ready for some questions, right, sir?
Yeah.
You can people who have questions, please you may raise your hand and we'll pick and choose, and you can ask the question directly to sir. I think DSX has a question in the chat that says, can spinning black holes produce similar results in terms of shape of orbits and waves?
Yeah. If we consider the spin of the rotating black holes, the similar kind of behavior is there. But if we go and consider this spinning charge, this particle, test particle. If the test particle are spinning, then the orbits are different. I mean, the orbits are same, but the associated gravitational wave appears to be very difficult, numerically very difficult to manifest, and nobody has accurately defined it right now. But yeah, but in the context of the spinning central supermassive black hole, the results appears to be same. Okay, I can see the second question here. How, if nothing escapes black hole, then how Hawking radiation occur? Okay, so basically I'm not aware about this Hawking's radiation, but the question I can answer this: how, if nothing escapes, then how this radiation is escaping? So I'm not exactly aware of this Hawking radiation, but I'll explain you this that how something gets out of the black hole. Okay, I have studied this very interesting paper. So what that paper defines is like mathematically what happens is let's say I have a black hole right here, and I have a particle, and it somehow goes and touches the horizon of a black hole. So from our perspective, what appears is that that particle went inside the black hole. But from the perspective of the black hole, from the perspective of this charged particle, I mean, we are considering the equation in terms of this charged particle. If you go, so for this test particle, if you go and study in terms of this test particle's time actually becomes zero as it touches this horizon. So in terms of this particle, what happens is that its time stops, and it stops its motion, it stops its everything as it touches the horizon. Now, as I have said, this radius changes with this charge, it changes with the mass. So let's say somehow the charge of a black hole, somehow the physical parameters are in such a way, like this horizon also depends upon this. Time will not exist from it. I will not say time will not exist. I will say time stops from its perspective, because time will exist, but its value will be zero. Okay, so but now this radius okay, this horizon, it can actually changes with the parameters. It can change with the dark matter environment. It can change with the extra gravitational pull which is there in the metric. It can change with the mass. It can change with the charge. It can change with the rotation. So let's say somehow this rotation and this other parameter changes. So the horizon can shrink or it can increase. Or if it shrinks, then the particle now will have time, because its time is not zero right now. So you can say, okay, now the particle has the capability to escape. So, like, yeah, okay, can you just wait for a moment? My roommate is here. He came from here. I need to open the door. Okay, so sorry, so sorry. Yeah, so sorry, so sorry. Yeah, where I was. Okay, so yeah. So now it has this capability to actually go and escape from the black hole. So I don't know about this Hawking radiation. But actually, I have studied it, but I forgot completely. I studied the thermodynamics of the black hole, but I forgot. But yeah, these kind of processes are there for the black holes. You can actually like, I believe you can find the question in the chat GPT or this AI as well. But yeah, this kind of thing happens. Like time changes from the perspective of the particle. Time stops when it touches the horizon. So this is there. Okay, what else I have? The other question is like how we came to know that dark matter is fluid from without even seeing it. That's actually a good question. And the answer to this is basically it's a model. So we don't know how dark matter behaves. We don't know how it is. We imagine, we assume that if dark matter behaves somehow behaves like a perfect fluid, then this is going to be the behavior. So it's basically an assumption, and if we have to go and like see whether this assumption is correct or not. We have to actually see how the gravitational waves are and other like gravitational lensing and gravitational the shadows. We have to analyze these observational things and with the theoretical, and then we have to see what kind of behavior the dark matter is. So for this, okay, so dark matter can be fluid, it cannot be. What we have done is basically we assumed it to be a perfect fluid, and we see the analysis, how the analysis is going. Okay, what else we have? It's very interesting. Can you share this RP? What's RP? Somebody said it, we share its effect and imagine or compare it with the fluid property. No, like it's like, yeah, I mean, I said it like we don't have this we don't know how dark matter behaves, but we assumed it and we considered it, let's say it to be as like perfect fluid, and do the analysis, and let's see how what theoretical model do we get, and by in future by observe by uh, connecting it with the theoreticals, we can find, okay, this is going to be the behavior. Okay, so we have other questions. Okay. Okay, now I can see like 59 messages are there. I would request host to actually sort these messages because I'm not very good in reading. Can you please do it?
These are most of them are not questions, sir. Tanya, you can go ahead and ask a question. You've raised your hand. If you're able to unmute, yeah, go ahead, please.
Thank you for such a session. Now, my question is that why does time slows down near a black hole? Like, why does it behave like a light, and why does it bend due to the curvature of black hole?
Okay, okay. So basically, the question why it is happening, then I'll say that this is because of the curvature of the space-time. Okay. The answer to this, why the lights bend like in between, when why the light bends near the black hole, I'm answering to this question first. It's basically because the curvature is now like the space-time is curved. So it's very difficult to actually imagine it. So you say now you have a road, straight road, and a car is walking in the straight road. Now imagine this road is not straight, it has a curvature. So the car will go within the curvature. Okay. So this is what light is doing. It is just following the space-time curvature. Okay. And that's why it appears to be bended. Because we are watching it from the perspective, we are considering this, we have this like idea, we consider the space-time to be flat. And that's why it appears to be bended, because it's the space-time which has curved. and light is just basically following its natural trajectory. That trajectory is basically called as 0 to 6. Okay, so that's why light appears to be bended. And your first question, your first question was why time? What was the question? I forgot. Why time something with the time? I guess.
Sonia?
Does it behave like light?
What light?
Like, does time behave like light near a black hole?
No, no, no. There is no correspondence between time and light. Time is basically okay. Uh, I believe most of you have studied these coordinate systems called as Cartesian, spherical, and Cartesian coordinate. Like when you go and plot anything, you say x and y. Okay, you plot between x and y, or we say the space time is x, y, z. Okay, any equation can be written as x, y, z. Now imagine there is no x, y, z, but x, y, z, and t. So time is not behaving like a light, but rather time is now the basic coordinate, which is actually changing, or which is how, which is what light is following now. So we say that okay, time is like time is absolute. Time is like continuously moving forward. It is not the case actually. Time slows down for some perspectives. Like if for a particle which is moving near to the speed of light, its time slows, and for a particle which is in heavily massed near the heavily massed object, its time slows, as you would have seen in Interstellar, I believe. Okay, time slows when we go near to the heavily massed things. So time is now relativistic. It is now the fundamental coordinate. So it is not something which is behaving like light. Okay, I believe it's
Thank
fine.
you.
Okay, welcome.
All right, Afaq, you can go ahead and ask your question.
Sir,
Yeah.
do you give any notes?
Oh, you are asking for the notes. Like, I'll share my PPT with this with the coordinators, and they will forward my PPT to you. The PPT itself consists some notes. It has one book in gravity. You can follow those as your notes. So this will be helpful to you.
Sir, and I know, sir, I know seeing class sometimes this time network problem.
What?
I'm actually unable to understand. I would prefer if you can type your message. It would be, I believe, some network lagging is there.
Okay, sir.
Hmm.
Till then, Nikhil, you can go ahead and ask your question.
Yeah.
Hello, sir.
Hello.
Sir, actually, when we say space-time curvature, like we are basically saying it based on the gravitational wave, right? Like due to the gravitation, the space-time curvature is being bent, right?
Okay, so you're asking like, is it because of the gravity the space-time curvature is bending? Is it your
Yes.
question?
Yes.
Okay. Okay. So basically, yeah, yeah. It because of the gravity, you can say, and why the gravity? Use if you no, you cannot go and say like gravity is creating the space-time. It's basically the mass. Okay, the more the heavier the object is going to be, if an object is very heavy, so it is going to bend the space-time more, and this bending of space-time is creating gravity. So you can say, okay, gravity is the curvature of the space-time now in general relativity, but gravity is not the reason of space-time. Okay, curvature of the space-time. Gravity is the result because of the curvature of the space-time. Okay, so this is the mass. The mass is actually creating this curvature, or the other things like this perfect dark matter, this charge, or this other spinning part. So these other things are somehow creating or varying the curvature of the space-time, and that curvature is actually creating gravity.
So, but when we see the space-time curvature graph in 2D and 3D, the graph entirely changes when we see it in 3D, right? Basically, it is being sucked up into itself, right? It's the space-time curvature when we see it in the 3D.
Okay, if you're talking about Minkowski space,
Yeah,
so
yes, sir.
yeah. So actually, that Minkowski space is not nothing to do about the space-time curvature. That Minkowski space basically defines. You can see what is this Minkowski space. So you'll see these two triangles. Okay, you go and see these two like these two things is there in Minkowski space. So what are these lines? So these lines basically defines light-like trajectory. So Minkowski space basically defines how, because it is impossible to basically map something which is four-dimensional. Okay, you cannot go and map something which is four-dimensional, right? So Minkowski space basically provides us the idea what kind of trajectory can a particle have. Let's say if I have a particle and it has a light, if it has a light-like trajectory, so what's light-like trajectory? When this time part and this space-time is basically equal. Okay, we say this dt square is equal to ds square, something like that. Okay, when these two things are equal, so the angle should be of this, the angle between this the time part and the space part. When the angle between the time part and space part is 45, or you okay, what's the plot of x equal to y? What's the plot of the x equal to y? X equal to y plot has this straight line. Okay, this is if it is my y and if it is my x equal to y has plot this like this. Okay, so light particles have time part a time where the time part is equal to space part, and that's why they're what do you call this angle? The tan theta is equal to 45 degree, and that's why we get this straight line. Okay, now we consider the space time to be like positive, negative, positive, negative. So it has like this. Okay, one part here, one part here, one part here, and one part here. And now if you go and do it for x and y, you'll find a cone. Okay, so you like I have this and I rotate it, it will become a cone. Okay, and that is what Minkowski space is. Okay, and this Minkowski space have this another part. The inner part of the cone is called as time-like trajectory. It follows the time-like trajectory where this time part dt square is greater than the space part, and this is the trajectory which is followed by planets. It is the trajectory which is followed by particles, planets, and all in curved space-time. And the outermost part of this light cone or this Minkowski space is the space-like part. Okay, so the space-like part is basically when the space part becomes dominant than the time part, and this space part is not something which is followed by anybody. So not like no particle and no planet follow this. So we are interested over this light trajectory and this trajectory and the part which is inside the Minkowski space. Okay, so this is basically the Minkowski space. So it is, I'll say it is that's why it is called as light cone. Okay, it is not something which defines the universe. It doesn't define the four dimension. It defines the motion of the particle. What kind of motion of the particle will be? Okay.
So even the Minkowski space gonna affect the light path.
With okay, you said Minkowski space affects the light trajectory. This is what you're saying.
Yes,
Okay,
sir.
so I think you don't get what's okay. If it is Minkowski space and trajectory of the trajectory of the light will affect it. Basically, the light trajectory of the light is defined by when the time part is equal to the space part. Okay, and a question like whether this trajectory of the light is okay. The trajectory of the light is affected by the curvature of the space-time. That's right. But is it affected by Minkowski space? Is Minkowski space equal to the curvature of the space-time? No. Minkowski space basically defines that what kind of different particles will follow what kind of different trajectories. This is what Minkowski space defines. So whether saying that okay, this light will be affected by Minkowski space, Minkowski space itself defines the trajectory of the light. So I believe that is your answer. But if you are asking like whether light is affected by the curvature of the space time, yeah, curvature of the space time it is affected.
Oh, thank you, sir.
Welcome.
All right. I think most of the questions have been done. Is there any other question somebody wants to ask directly? Right, I think not so. It has been a wonderful session, by the way, sir. I joined in the second half. It was wonderful to watch you explain so many topics. Absolutely great. I think people don't have any more doubts, right? Okay, Shrita, you can go ahead.
Hello. So I have a doubt. So the slide shows that PFDM changes the orbit and energy a lot. Can we tell from gravitational waves if a black hole has PFDM around it or not?
I don't get the question. Can you please repeat it again?
No, the slide shows that PFDM changes the orbit and energy a lot. So can we tell from gravitational waves if a black hole has PFDM around it or not?
Okay, like can we see from the gravitational wave whether the PFDM is there in the universe or not? This is your question.
Yes.
Okay. So let's assume like Lisa, like it went today, it went tomorrow, and start observing and observe some gravitational wave. Whether by seeing those gravitational wave will be able to find out whether there exists dark matter or not. And I believe, yeah, we can somehow explain this. So, but it will be very difficult. Not today, because theoretically we are not very much. Because you know what happens. What is going to be the process? I'll explain. Okay. So let's say, but for let's say I have some real gravitational wave, and by looking it, how can I say whether the environment going to have dark matter or not? So one way is to manifest a theoretical gravitational wave. Okay, and that becomes very difficult. Why? Because in theory, then we have to consider all the parameters, we have to consider all the models, and we have to consider everything. We have to consider spin, we have to consider acceleration, we have to consider other particle environments, string environment, and other environments. Okay, except this dark matter parameter. Okay, we consider all the parameters. Okay, and then we manifest this gravitational wave, and we sort of compare it and see okay whether there is this reflection or not. Okay, and that is also become very difficult because we have for the stringy particles we have like so many models. Even for the accretion disk manifestation of accretion disk with this dark matter, it has so many models. So for doing each and everything, we have so many theoretical models. That's why it becomes very difficult to manifest theoretical model. Okay, but so what we can do is like there can exist some other methods to verify the behavior of the dark matter. The first one is like by seeing the how the velocities or velocity distribution of different planets is there in the galaxy. I believe by sort of seeing the gravitational lensing, we can get some idea about the dark matter and other things. So other observational things are there. And you know what? Even some laboratories, some in Taiwan and few in India, I guess, they are actually working in this particle observation of the dark matter. So what they are doing is like they're doing some sort of experiments to kind of observe these dark matters. So Taiwan, some groups in Taiwan are doing this. So you can see, but from the gravitational wave, it will be very difficult to actually to actually detect this dark matter.
Okay, sir. Thank you so much.
Great. Right, I think we have exceeded the time limit. We have, I think, and all the questions are also solved. I think we should end the session here, sir. By the way, it was absolutely a treat of a session to watch. Last session was also really, really good, and this one as well. Thank you so much, sir. We'll end the session right here. Thank you everybody for joining in. We'll see you in the next session for the clubs and for the summer schools. Thank you everybody.